What's up, science lovers? I'm Ria, one of your cafe coordinators, and we're back with our Teen Science Cafe presentation. We're excited you're here, and please be respectful during the presentation and save questions for the Q&A section. You can check out Teen Science Cafe Raleigh on Facebook and Instagram. We'd love it if you followed us to stay up to date with more amazing cafes. You can also view our YouTube recordings of this Teen Science Cafe and past cafes on the museum's YouTube channel.
Our presenter is James Chapa, a food scientist from Enzymes. He works to improve the flavor, functionality, nutrition, and consumer acceptance of plant-based foods. Mr. Chapa has been with Enzymes since 2020 and has a background in food science research and development. Please welcome Mr. Chapa to the stage.
Thank you. How's everybody doing? Yeah? Let's keep the energy up here, because I have the pleasure of talking about something that I'm really passionate about, and I think you're going to know why pretty soon. But first off, what is this food science thing? How many people really know what that is? Well, that's more than what I usually encounter, so I'm really impressed. This is a good audience. So I'll tell you a little bit about why I got into food science to begin with. When I was growing up, there were a couple of really great shows on the Food Network called Good Eats and Unwrapped. In Good Eats, Alton Brown is sort of explaining how food works, scientifically speaking, and it's not always entirely correct, I realize now, but still it got me interested in it, in food chemistry, and sort of picking apart how good food is made. And then Unwrapped was a great show with Mark Summers about manufacturing of all sorts of different foods like Twinkies and what have you, really healthy stuff. So that sort of unlocked a passion to learn more about how food works. And of course, I also enjoyed science. And another good thing about being a food scientist in general is that food isn't going away. Everybody has to eat it. And we need to eat it pretty much daily to survive. And so there's plenty of jobs to be had related to food and science. And then also, we have a pretty important mission still in terms of making sure that we can keep our food system producing enough food for the growing human population, and then also trying to make sure that that is healthy and sustainable as well, right? And that we're not wasting too much. And so the food industry hasn't always delivered on that mission, and I think it's received quite a bit of criticism over the years. But sort of my generation of food scientists, we've been able to sort of work on fixing things and getting things back on track, I would say. And so when you start to unpack what food science actually is, it's not like no food scientist will be exactly the same as another food scientist. We all specialize in a little bit different subfield within food science, right? There's food chemists, food microbiologists, food engineers. You could build a whole career just specializing on one particular type of food. You could become known as the world's foremost cheese expert, for example, or maybe you're a bakery scientist. And so that's what you decide you want to get into. And so it's really, once you start into the path of food science, you sort of figure out what it is that you like. And in my case, I started out down the road at North Carolina State University in 2012 and graduated in 2015. I had the opportunity to do a little bit of undergraduate research, working on something called texture analysis, where you're looking at the physical performance of food, sort of predicting how it's going to behave in your mouth when you eat it. And so that led into the job that I then took in St. Louis, where I worked on pizza, not specifically, but I worked on cheese and bakery product and processed meat in that position. And then I went to Purdue University, which is in Indiana, for my master's. And there I dabbled more in food engineering and also this thing called life cycle assessment. So I have a couple of publications that are life cycle assessments, and that is everything to do with sustainability. So in that sense, you're looking at inputs and outputs and emissions, and really comparing. You can compare two different types of foods to each other and seeing which one might be more sustainable. You could identify hot spots within a particular food product or manufacturing process in the endeavor of trying to improve them, so making it better in some sort of way. And so that's what I did during that time, and it was a little narrow and deep, but then I went back out to the industry and got a job in California where I was working on tortillas. And you might be like, well, what's so complicated about tortillas? Why does anybody need to work on that? But it's actually a lot of things, because there's many different types of tortillas, actually. So you can have tortillas that are supposed to be white and fluffy and soft, and those are great for like street tacos and such. Or you might have a tortilla that needs to be pliable and not absorb moisture. It needs to have a certain set of physical characteristics so that it can function well as a wrap, and then moisture doesn't migrate from the components that are inside the wrap to the wrapper. So, and the way you make those two tortillas and the ingredients you use are going to be very different. And so that's why somebody needs to do a job like that, actually. In any case, I joined Enzymes in 2020. And since that time, I've been working on plant-based foods. So think plant protein, anything from legumes primarily, also grains like rice and wheat, and plant-based milk, so primarily oat milk, and then plant-based meat, quite heavily lately. And if we look at a day in the life of a Novozymes tech service scientist, it is quite a bit of travel, actually. So last year was 25% travel. That was 59 working days. It took me to a lot of cool places, including Copenhagen, Denmark, which is what you can see in the top left picture. That's Nyhavn Canal, the bright, colorful one. It's very nice. And then the nice team of people there that's a group of scientists that we were all working on new plant-based meat projects together. So it was a lot of good collaboration. And then next to that is our regional headquarters, which is up the road north of here in Franklinton, North Carolina, actually. And so we actually have a full production facility there where we make enzymes, and I'm going to tell you about how we do that shortly. But then we also have a very nice set of laboratories and different industries that work there. So it's a good place to work as well. And then the middle row of pictures, that is sort of one project that I executed a while ago, and it was everything to do with oat milk. And so we actually analyzed a lot of oat milks that were out there on the market. We made them in the lab, and then I also got some stuff published at the end, and so it ended up in a good magazine. And so in that picture you're seeing, I'm very happy to have published that and to get the circulation of that and notoriety for Novozymes. And then bottom set of pictures is sort of laboratory plant-based meat. So looking at making a burger sort of like an Impossible Burger. And then if we pick apart like a day-by-day basis what a scientist at Novozymes is actually going to do, a lot of it is project management, because we have a number of different customers that we support, and so they all have active projects, or we want them to have active projects. And so it's a matter of managing those projects and keeping them moving forward so that we achieve objectives, right? And then problem solving is really key. Designing experiments, executing experiments. The travel piece is, a lot of it is to visit customers, maybe working with them in their factories or their labs, or going to conferences. So I think I went to 4 or 5 conferences last year, oftentimes presenting work at them. So, you know, doing presentations kind of like this, but maybe a little bit more technical, and sometimes even less technical, because the objective is to sell product, essentially, for the company. But now it's time for a question. And I might not have set you up for this well, so if you get this right, kudos. But who has a guess here? What specialty within food science designs and executes taste tests? And multiple choice. That's a good guess. Not the answer I'm looking for. Sensory science? Sensory science is the correct answer. So, very nice. So if you're interested in taste tests, you can become a sensory scientist by training in food science, and you will, of course, need to do some food chemistry because a lot of flavor is based in chemistry. But then the objective of sensory science is quite often, you know, is this particular food product better than this one? Or do people like this one better than this other one? Or let's say that we want to switch ingredients. We find an ingredient that does something similar but is a little bit cheaper. Could we switch it out and no one would notice? And so then you need to be able to test that too. And so that's why sensory scientists have jobs. Okay, now it's enzyme time. And you might already know some of these things, but enzymes are essentially nature's tools for speeding up vital biological processes. They are pure proteins. Now, if you take a biochemistry course, you may have a professor who tells you that enzymes can also sometimes be RNA, and that is technically true, but we don't have any of those industrially manufactured. So all of our enzymes are pure proteins. They are present in all living cells. They help digest food, for example. They are catalysts. We can speed up chemical reactions. And what this enables us to do is really to eliminate harsher chemistries. So we can use mild reaction conditions, usually very mild temperatures and neutral pH, to achieve the objective. And this can save time, energy, and water. The reactions that enzymes catalyze are highly specific. And the enzymes themselves are fully biodegradable, so they break down to harmless amino acids. And a little bit more technically, what happens with an enzyme, that protein binds with its substrate and the active site, forms an enzyme substrate complex, and then you have a reaction product. In this particular case, it's breaking it apart, so the substrate goes in and two things come out. There's also enzymes that join things together, and I have an example of that coming up soon. And now, if you've been alive in the world, there is like a 0% chance that you've never interacted with an enzyme, an industrial enzyme in one of many of these different applications, because they're used in so many different products, actually. So if we just talk about milk, if you want to have lactose-free milk, let's say you have lactose intolerance and you need to get rid of lactose, well, the best way to do that is to use a lactase enzyme to break lactose into component sugars, glucose and galactose. Or you could avoid dairy milk entirely and have oat milk, for example, and the only way to make that is with enzymes. If we talk about bakery product, the best way to keep bread fresh and to extend the shelf life of bread is to use enzymes that change the structure of starch that keep it from retrograding or staling over time. If we talk outside of food, we could talk about laundry detergents. So anything that has a stain can be broken down essentially with an enzyme, and that is the best way to do it. And so very good laundry detergents will often have quite a few different types of enzymes for the different types of stains that are typically encountered on clothing. That's also true for dishwashing and other types of cleaning applications, even medical cleaning. Biofuel is another area that really needs enzymes to break down those materials that are used, like corn stalks and sugar canes and what have you, to be able to make fuel out of those types of materials. Another application is animal feed, so liberating more nutrition out of the animal feed. Now we can talk about how the enzyme products are made, and we have so many different ones. In fact, that's one of the more challenging aspects of being a scientist at Novozymes, is just getting your head around our broad portfolio of different enzymes and maintaining the product knowledge. But essentially, what happens is there's a production organism, there's a particular type of cell that makes the enzyme that we want. And that is maintained in a vial in frozen storage in a very pure state. And what will happen is a group of scientists will take those cells and then start growing them up into larger and larger fermentations. So they get fed material so that the cells grow, and then eventually the fermentation reaches production scale, which is going to be, hundreds of gallons in a hydroconical fermenter that takes up a lot of room. And we have a number of them at the plant in Franklinton. And essentially, once the cells grow, they start to secrete the enzyme protein outside of the cell, where it can then be recovered so we can purify it. We get rid of everything else that's in the broth. So all of the dead cell material is removed, and we end up with just the enzyme protein. So there's a series of filtration steps that occur. And then, once you have the enzyme protein, you need to standardize the activity so that it's always the same. And that way, our customers always get exactly the result that they're after when they dose the enzyme. And then also stabilize it so that it doesn't lose activity over time. And that's really important, actually, because you could have an enzyme that's great, but if it's if it's not great, as good next week as it was today, then that's not really useful out in the real world. And so here's an example of what one of our products looks like in a liquid format jug. Oh yeah, and you can, once you've done that, you can sort of have enzymes that are sold as powders, or they can be sold as liquid form. In food, we typically use liquid, with the exception of bakery product, where they like powder to go in with the flour. Now, let's tie this back into food real quick. And one of the ways to set this up, we need to think about what food actually is in terms of building blocks. And you'd be hard-pressed to find a food that didn't have at least one of these components in it. And usually they have a mixture. So there's some foods that are higher in some of these components than others. But if we talk about water, it's not something to be taken for granted. It's the universal solvent of life. It is quite an interesting little molecule in terms of what it does at different temperatures. So if we look at ice and liquid water and then steam, there's a lot of different things to look at, actually, with the water molecule. And then what water is doing within a food is called water activity, and that relates to microbial growth and also to shelf stability over periods of time. So it's actually quite important to study the impact that water has in foods. And there are people that specialize in just that. And then if we talk about a little bit more complicated, we add a carbon molecule. We're talking about carbohydrates. And so the simplest carbohydrate is going to be C6H12O6. And depending on how that gets configured, you're going to have different what we call monomer sugars, one of which is glucose. And so that's a particular way that those atoms get put together. If you put the atoms together a little bit differently, like it can be exactly the same formula, but now that it's a different shape, it tastes different in your tongue, and it actually will be metabolized differently by your body as well. So it's very interesting what happens when you start putting atoms together and things get more and more complex. Lipids, so that's fats and oils. Here we have a typical one in food would be a triglyceride, although you can also have phospholipids and things like that. But triglycerides, you have a glycerol backbone and then some fatty acid chains. Those could be saturated or unsaturated, and we're going to come back to that in a second. Protein, you might be able to tell that's my favorite one. But I quite like protein because it's a very big building block. And also, it's comprised fundamentally of the like 20 or so amino acids that get put together in all sorts of different ways. And then those proteins can get folded up in all sorts of different ways. And there's some very fundamental differences between animal protein and plant protein. But one of the hard jobs that we have is trying to get plant proteins to function a little bit more like animal proteins in some of these products. And so that's very, very interesting stuff. And now, that kind of sets the stage for what enzymes are doing in food. So why would we want to use enzymes in food? So it's really these three pillars of usability, precision, and in situ. So when we talk about usability, oftentimes it's softening materials for easier handling, solubilizing material, improving the digestibility, maybe improving the palatability or how something tastes, maybe improving the nutrition profile, and then this concept of upcycling. That's where you take something that used to be a byproduct or a waste product, and now you're able to make a value-added food with it that's actually very high value. A really great example from, it's an older example now, but whey protein used to be the byproduct of cheese manufacture, but now it's worth more than cheese. It really became, we realized how nutritious and valuable it is and how to process it properly. Precision, that's really the fundamental benefit of using an enzyme versus another approach to a problem. It's because enzymes have a substrate, like we saw, and that they're specific for, and then they're going to do that specific reaction and create that specific end product. In situ, I have an example of this coming up, but it's really talking about valorizing a component that already needs to be in the food rather than trying to add in something else. And so that'll be clearer after the example. And then key classes of industrial food enzymes. You do not need to remember this list of names. However, the key thing to keep in mind is some of them break stuff apart and some of them put them together. So on the left, we have the enzymes that break down components, and on the right, we have those that modify or join molecules together. And sort of the names kind of do make a lot of sense. So proteases break down proteins, amylases break down amylose or amylopectin, which is starch, cellulases break down cellulose, xylenases, xylins, and so on. Now we get to talk about plant-based foods, but first a question for the audience. What is your favorite plant-based food category? And maybe the way we should do this is I want to see a show of hands for each one. So we'll go one by one. Hands for plant-based milk. You guys counting the hands over there? We need to see who the winner is. Good. All right. Plant-based yogurt. Two hands. All right. Plant-based cheese. One hand for plant-based cheese. Ooh. Plant-based meat. All right. A little bit better. Is there anyone in the yuck, I don't like plant-based at all category? Two? All right. Well, we're going to start off with plant-based meat. And I'm not going to read everything here for you, but the key thing to keep in mind when we're making plant-based meat is we have a goal. And the goal is to make this product essentially as meat-like as we possibly can, realizing that our starting material is nothing like meat whatsoever. So we remember those plant proteins are nothing like animal proteins. So how in the world are we supposed to achieve this? And they are getting close. We have made strides. And one of the things is this technology called extrusion, which helps to restructure plant protein into a more fibrous state. So that's one thing. But then also mindfully putting together components so that you end up with similar macronutrient compositions, but then also the structures. So if you look at the structure of animal meat under the microscope, like these images are showing you, you can see that muscles, they have fibrous structure, right? And that's because they can contract and relax, and they move an animal around, and then that structure is maintained in the dead flesh as well. But then we can try to mimic that with putting together these plant materials. And so we need to look at things like network structure, the particle size and morphology, what the oil and water phases are doing in the product, and then the connectivity between the phases. And so now I also want to tell you what all these ingredients in plant-based meat do, because these ingredient statements do tend to be rather long, and that's because you need different components to do different things. And so if we start out with this example of an Impossible Burger here, and I think there might be plant-based meatballs that are going to get circulated as well to the audience. So if so, now would be a good time. But if we look at an Impossible Burger and we look at the ingredient statement, you can see that water is number 1. Oh, and if you didn't know this already, anytime you see an ingredient statement, the ingredients at the top are there in a greater proportion than the ingredients at the bottom. It goes from more to less. And so we can conclude, you know, there is mostly water here, and after that, it's the soy protein concentrate, and so that has actually been, part of that has been extruded into what's known as textured protein, and that provides the bulk of the material, and it actually will hold on to the water pretty well, and so it gets hydrated up. And then there's 2 different kinds of oils. Can anyone tell me the difference between sunflower oil and coconut oil? Maybe with a microphone.
You can raise your hand if you have a guess.
Is it the fat content?
So they're both fats. Well, technically one's an oil and one's a fat. But what, even though we call it coconut oil, but what, and you know, what difference am I getting at when I say oil versus fat? Any guesses on that?
So coconut oil is actually basically the nut, the fruit called nut, right? The flesh of the, that's from the flesh of the coconut.
Well, it's refined from that, yes.
Yep.
Yeah.
And sunflower oil is from the seed of the sunflower.
Correct. This is true. The other thing that's interesting about them is that one is primarily an unsaturated fat or oil, which means that it will remain liquid at room temperature, whereas the other, the coconut oil, is a primarily saturated fat, and that's why it's solid at room temperature.
Got it. Okay.
And so it has to do with those, the linearity or kinks in those fatty acid chains, and how the crystal structure can pack together. And the way to go from one to the other is really to change the temperature. So I think we all know that if you want to create liquid coconut oil, you have to heat it up, right? But in this case, they use that coconut oil to create the white flecks, or what we call marbling fat. So that remains solid and doesn't dissolve in with the rest of the material, whereas the sunflower oil is going to go in there to provide sort of the characteristic mouthfeel into the rest of the formulation. Now, I also highlighted something called methyl cellulose, and this is an interesting ingredient because it's present at less than 2% of the formula, but it does a really important job. In fact, it will gel as the product is heated. So it's a liquid form when the product is raw, but then it starts to firm up as the product is cooked. And that gives you sort of a meat-like texture response as you cook this product. Now, there are other ways to do that, and in fact, it's what we've worked on a lot at Enzymes, is how can we get the texture that we're after without having to use an ingredient like methyl cellulose? What if we could just modify the soy protein concentrate to achieve a similar objective? And so that's what we've spent a lot of time working on. And then I also highlighted this big list of micronutrients. And it's nice that they put them into the product because this, in a lot of plant-based meat, these are missing compared to traditional animal meat. And so particularly B vitamins are one reason that beef is recommended diet, to have in your diet. But if you can get it fortified like this, then that's also a nice option. Oh, and another thing that we can do, and maybe you know this already, but any ingredient statement and nutrition facts panel, you can always do a little bit of math. So back of the envelope approximations, if you will. But they're listing the amount of fat, carbs, and protein, and that means you have about 41, if we sum those up, we have about 41 grams of those macronutrients, and that means not counting the ash, so things like sodium and calcium, which are there in very small amounts, so we can pretty much ignore them for the purpose of this calculation. But not counting the ash, basically we have the serving size minus the other amount of stuff, so the fat, carb, and protein, and that gives us the total amount of water that's in the product. And so then we divide that through by the serving size, and that gives us 64% water, approximately. And lo and behold, if you Google what the water content of real beef is, you find 64%, at least for 85% lean product. And so it actually will vary based on the amount of fat content that's in that beef. But, obviously this wasn't an accident. We are deliberately targeting similar macronutrient profiles in these types of products. Now this gets to the point I was telling you how at Novozymes we're trying to use an enzymatic approach to get the texture that we're after. And so the key here is to use one of those enzymes that joins things together. In this case, it's a cross-linking enzyme that cross-links protein. It's called microbial transglutaminase. It joins proteins up at glutamine and lysine locations. And so we can use this enzyme to generate texture and to create consumer appealing labels because we are able to remove things like methylcellulose and carrageenan and other hydrocolloids. And I told you a little bit about this before, but carrageenan is one of those hydrocolloids that can gel things when it's cold. If you look at the top, that's the cold state. The bottom row is when it's heated. But carrageenan wouldn't be very good if you need to have texture when the product is hot. And so many products will actually use a combination of carrageenan and methylcellulose if they need to have both cold and hot firmness, whereas with the microbial transglutaminase product named Vertera Probite, we can actually have stable texture or gelation at both temperatures. So because it's a covalent crosslink, we have essentially a very similar texture in both the cold and the hot state. And if you look, the liquidy, it's liquid in both pictures, top and bottom. That's the same protein with no enzyme. So it's exactly the same otherwise, it just didn't get any enzyme to cross-link the protein up. And we can also look at this in further detail under a confocal microscope, which is very nice for being able to image different fractions. So in this case, we stained the protein and the oil, and we can image what's going on in those phases at a high level of detail, and then also at different temperatures. So whether that's room temperature, up to cooking, and then back down to cooling. And top row, you see the blank, bottom is the enzyme treated. So otherwise, they're exactly the same amount of protein and oil, water. And so what you immediately will notice is it looks like there's more oil in the enzyme treated condition, but that's not true. It's just there's more oil droplets and they're smaller because it's been better emulsified by modifying the protein. And it's also more stable to coalescence. And here, this is a video, and it's showing you the importance of selecting a good protein substrate for the enzyme, because it's exactly the same amount of enzyme and the same amount of protein in each of the wells, but the end texture is very different. The what? The type of protein. Yeah. And so when we talk about type of protein, there's a dozen or so different protein suppliers across the world. They all will intake things like soybeans or peas, and then they process them in a plant and by virtue of how they source their peas and the process that they execute, they have different functional properties at the end. So sometimes they get damaged or broken down, and that means that when you cross-link them up, you might not get as good of a gel structure out of them. But it's also quite difficult to just look at a protein powder and know what it's going to do. You need to be able to test it. And so that's what this assay was developed in order to do. Now this is going to show you, yeah, here we go. Lag. Should we move on, control room, or do you think we can get the lag under control? All right. Well, trust me, it was really cool. Actually, my clicker's not working. Oh. Okay. Oh, too far. All right. Oh, all right. Here we go. So we can make more than just burgers. We can do hot dogs. This is some work that I did personally up in Boston. It was quite fun. So we made plant-based hot dogs using the enzyme from start to finish. And once you have the hot dogs themselves, there's all kinds of tests that you can do with them as well. You can kind of compare them to regular hot dogs in sensory studies like we were talking about before. You can measure them on things called texture analyzers to see how the texture actually is similar or different. And then you can be like, well, actually, these could have been a little bit better, and so then you're going to redesign your experiments for next time and tweak your formulas. We also have done plant-based meatballs, and these we did down the road at NC State, actually. So these images are from NC State Food Science Meat Lab. You're looking at a ribbon blender with the TVP, that's textured protein, textured vegetable protein. We rehydrate it up with colors and flavors. We add the functional protein and the enzyme, and then we can form it into meatballs. Aha, meatballs like these meatballs. And did everyone get some too? Yeah? Cool. Who knows the answer to this one? Who wants to guess? Oh, okay, yes. Yes, 100 points. Very good. So the correct answer to what does microbial transglutaminase do is 4, cross-link protein. And it's by virtue of cross-linking protein that we can use it to create texture and desirable eating experience in plant-based meat products. Now we're going to switch to plant-based dairy, and I think there might be some oat milk samples for the audience. And the first question is, how do you go from oats to oat milk instead of oatmeal? Can anybody tell me the correct answer? Yes. Yes! 100 points! The correct answer is enzymes. Right. So let's take a step back and look at what oats are. So primarily they're starch. There's also protein, around 10%, maybe a little bit more sometimes. But the vast majority of an oat is starch. And starch is interesting because it's this highly ordered structure, crystalline, amylose, amylopectin, and those are chains of monomers, glucose, and then glucose, two glucoses is a maltose, and then so on and so forth. But the deal is, to make oat milk, we need an enzyme that can break starch down. And the best type of enzyme for breaking starch down is what's known as alpha amylase. And so it can actually take amylose and amylopectin and chew it and turn it into dextrins. And so dextrins are simply a little bit shorter units of these glucose molecules. And they can have branching points. That's one of the key differentiators between amylose and amylopectin. Amylopectin has more of those branching points. What we can also do is utilize an enzyme that generates sweetness. So in this case, we call it saccharification. And so here we're looking at specific types of amylases that like to generate maltose or glucose. And the different oat milk products that you have on the market have different amounts of glucose and maltose by virtue of what specific types of enzymes they utilized. And so that's going to actually impact their flavor and their sweetness profiles too. Now hopefully this one works because it's really cool. But what you're looking at here is basically oat flour in a big tank of water that's been heated up, and now we add the alpha amylase. And what you're seeing, is a super rapid reduction in viscosity, actually. Nothing changed in terms of settings on the mixing. So it was mixing with the same torque as before, it was just the viscosity of the liquid rapidly decreased because of the action of the enzyme. Now we can also do that at a smaller scale in the lab, and that's really useful if we want to try out different things and then measure what we're getting. And so we can build out what we call dose response, and we can understand very well how adding a particular enzyme at a certain level is going to create a response in terms of the sugar and the viscosity that we get in the finished oat milk. And so it's nice to be able to do that. And then samples from that type of work can also get put in front of panels in taste tests by sensory scientists. And so we've done that type of work as well. This was a project I worked on in terms of trying to get specific sugar levels in the finished product. And so if you look, comparing these 3 fact panels, we had an 8 grams of sugar per serving, a 4, and a 0. And there are actually commercial products out there that are exactly like this, including Oatly is going to be in that 7 to 8 grams of sugar per serving. Planet Oat is the 4, and then you've got some 0 sugar products on the market as well. And so we understand how to do products like that at Novozymes. Another thing that we did was to actually do the sensory science on these types of products. And this type of plot is really typical for food science, sensory science. It's called the spider plot, and what you're looking at is these different attributes. And believe it or not, they actually, when a panel becomes trained, they can have a quantitative way of identifying each of these things. So the scale actually goes from 0 to 15, and it's, you know, a 15 would be a highly intense, let's say that it's sweet taste, 15 would be really, really sweet, like sweeter than Coke, whereas 0 would be like water. And what we were looking at was how similar we were for one, and then also how similar we were to actual dairy milk. And so in this case, the 4 grams of sugar and the 8 gram of sugar oat milks were very, very similar to each other and also to dairy milk. So they scored about a 2.5, and dairy milk is a 2.3 on this intensity scale. And there's other attributes that we were looking at. Viscosity is a key one. Some of these others are interesting, but they weren't really what we were impacting with the enzyme so much. It was, you know, this is the starting material that we have. The enzyme is more about creating sugar and liquefying the product, reducing the viscosity. And so, who can answer this correctly? The question is, what are 2 benefits of using enzymes to produce oat beverages? I see a hand. Can the hand get a microphone, please?
Is it A?
No, not the answer we're looking for. Next hand, please.
It's B.
That's right. Although D deserves partial credit as well. Particularly in light of this is going to be the final slide actually, but foaming improved by enzymes. So in this case, what we've done is to actually modify a different component of the oat. Like I said, there's some protein there as well, and so you can use a protease that will actually break down the protein. In this case, we use a very selective one that only breaks down the protein a little bit because we don't want to totally break it down. We just want to break it down enough so we enhance its emulsification or emulsifying capacity, and that's what's going to give us the ability to retain those air bubbles that are the foam, essentially. So, and the retention of the foam is what makes it great for latte art in particular. So any type of barista application, if that's what the oat milk is supposed to be used for at the end of the day, then this is a great option in order to get more foaming at the end. And I'll probably take a second in case you wanted to use the QR code or to know what our website is, but here it is, novozymes.com. It's pretty easy. We have solutions and active projects in each of these areas: plant-based dairy, the ingredients, so think plant proteins and starches, and then also plant-based meat and culinary.
Thank you, Mr. Chapa. Food can be fascinating. It's time for the Q&A. Raise your hand and look for the cafe coordinators with purple shirts who will bring the microphone to you. Please wait for the microphone to ask your question. This is important not only for our guests in the cafe, but our online viewers as well.
Oh, this is being filmed. I didn't know that. Yeah. Hi. This is, yeah, out of curiosity. Does your company only work with food, or do you also do like the laundry detergent enzymes?
Great question. Yeah, we work with everything. So we have a huge business in the laundry detergent enzymes, huge business in the biofuel, and we also have stuff that isn't enzymes. So we have specialty vitamins like K2, and we also have probiotic organisms, so actual microbes that are good for your health.
So what type of education is required to get into the enzyme manufacture field and industry?
Let me see if I understand your question. Are you more interested in actually growing the enzymes and producing them in the plant, or doing something like what I do?
I guess both, like either or.
So if you want to do what I do, then doing something like what I did and becoming a food scientist by training certainly is a good approach. You could also go into chemistry or biochemistry. More specifically, you could do chemical engineering. That's a really great field too. If you want to do more of the fundamental research in terms of going out into nature and finding new enzymes and figuring out how to grow them or to modify the enzymes with protein engineering, then you're probably going to want to focus on microbiology and also any type of biotechnology. Like NC State has a really good BTech center, so getting trained in that would be very useful. Further education would be really helpful. I think a lot of scientists at Novozymes have PhDs. I have a master's. That's pretty typical for people that do tech service in food. But if you want to do the more fundamental research, then you probably need to get a PhD. Yep.
Do you tell when you're putting more than one enzyme into something, like, for example, the oat milk, the one to decrease the viscosity and the one to make it foam, do they ever, like, contradict each other or interact in interesting ways? How do you deal with that?
Oh, that's a really, really good question. So if you add more than one enzyme, do they contradict or interact in interesting ways? And what I will say is, let's take the case of laundry detergent. There's multiple enzymes there, but in that case, they've sort of put a pacifier on some of the enzymes, like proteases, that would otherwise go and start eating some of the other enzymes, because the enzymes are protein, right? And so you wouldn't want your protease to eat your lipase or whatever until the final application. So in food, we can't use pacifiers like that because they're not food grade. And so we don't ever really put blends together that would have a protease and some other type of enzyme as a product that we sell. That doesn't mean that you can't use them together in an application, though, because when you think about adding the enzyme, let's say we're in the oat milk example still, then we have, 25% of this tank is the oat flour, and only like less than 1% is going to be the enzyme that we're dosing. And so there's just so much more substrate for each of those types of enzymes to go after that the impact that a protease would have on the other enzyme is negligible, actually. And so we really never see any kind of issue adding more than one enzyme together in a final application. And there are several applications where we would want to have both. So for example, that foaming enzyme, you would add that after you've added that liquefaction enzyme and started to solubilize the starch in the oat.
So I had a question about your slide that was discussing the macronutrients of the Beyond Burger. And you said that just for example, you added up and it was 64% water. But that was similar to the amount of water you would see in a certain fat level of meat. I believe it was 75%.
It was 85-15, actually, yeah.
How do you decide where to target your macronutrients to? For instance, I prefer a different level of fat in my ground beef, essentially as little as possible. So how does that change as you change the fat level within the ground beef, and how do you adjust the Beyond Burger to that, or how do you choose where to focus your macronutrient combination to get the flavor that you're looking for?
Yeah, that's a hard question. It's a very good question. So how do you come up with a product concept? And a lot of that will be driven by marketing, and so what consumer testing, what the concept needs to be. And so, but if you look, a company like Impossible actually has different SKUs or stock keeping units where they have different nutrition profiles. So they even have one that is lower in fat, and it's been certified by the American Heart Association. It's the Impossible Light, and it has less fat than the flagship version, right? And so, and that also gets back to sort of that different sugar contents in the oat milk, right? Some people are going to favor the one that's zero sugar just for nutrition, even if it doesn't necessarily taste as good as the other two, right?
On creating plant-based food options. They add different enzymes to make it more like meat, real meat, right? So the digestion processes and how they react with our body must be different between the plant-based foods and the meat-based foods, right?
Yes, 100%.
So what are the side effects that we might experience when we're eating plant-based instead of meat?
Oh, what a terrific question, actually. So, and it has no simple answer, actually, because food is, one of the complex things about it is there's this whole field called metabolomics. And so when you eat any particular type of food and break it down, what ends up happening is a cascade of hundreds of different compounds are created in your body. And to be honest, nobody really fully understands the complete impact of that yet. So, but one of the things that we look at a little bit higher level is just, what's going on with the total amount of protein, what's going on with the amount of saturated and unsaturated fat and cholesterol, we can say pretty confidently that you get less dietary cholesterol from these plant-based products than you do from animal product. However, on the downside, those proteins are less digestible than animal proteins, typically, and they also get metabolized differently. They have a different impact on your gut microbiome. So, it is quite a complex question.
I have two questions. So one of the questions is, when you're making oat milk or almond milk, do you guys make it all the same way, or there's different ways to make it?
Yeah, there totally are different ways to make it. So you can have different raw materials. So, it could be something as simple as this company buys from that farm and this company buys from another farm, or they buy from one part of the world, or they buy a different variety. So the starting material can be a little bit different. There's, dozens of different varieties of oat out there, for example. And then the specific recipe that they use, the water can be different. The dosage of the enzyme, which enzyme they choose to purchase, the reaction conditions, so the temperature and pH that gets utilized, and then just specifically, the goal usually is to do something a little bit different from your competition, right? Nobody wants to be exactly the same as anybody else, unless, they have to have some way of differentiating themselves. And it's better to differentiate on quality than it is to differentiate on price for long-term success.
Okay, so when you're eating foods and stuff, how does your body make you actually taste how it's supposed to taste?
Okay. So your tongue has a certain types of receptors that bind with particular chemicals. And so that gives you the fundamental tastes, essentially, of, let's see if I remember this correctly, sweet, sour, umami is one, salty, bitter. And actually, there used to be this thing called the tongue map, where different regions of the tongue had different receptors. That's actually not true, because the receptors are everywhere in the tongue at the whole time. So you actually can taste all of the fundamental tastes everywhere in the tongue. You also have a very important, they call it olfactory response, where the volatiles in the food actually would go into your nose. And so a huge part of what we consider taste is actually due to that, because your nose is quite sensitive to all of the hundreds of different types of flavor compounds that there are.
I have a question, two of them actually. So, right here. One is, so for vegetarians, right? I know you guys are making products that taste more like meat. But my wife is vegetarian. She's on the yuck category. So, what are you guys doing for vegetarians that would like to have protein that tastes a little differently? And then I think the second part of this question is, why are we doing so much work with different proteins out there? Just more fundamental in how animal protein is, getting more expensive, more carbon footprint and things like that.
Okay, I'm going to start with the second question. So why are we doing more with plant protein now? And a lot of it has to do with sustainability. So if people can consume less animal protein, then there will be fewer emissions and less impact on global warming. That is a position. And so there's a lot of research interest in doing more with protein. There's also a lot of opportunity, because there's, the protein is there, and many times it has been in the past a byproduct of manufacturing something else. So like starch for making corn chips or potato fries or what have you, there's been this protein that's essentially been thrown away. And so what valuable thing can we do to upcycle it? That's another very good thing to do, I think. And then I believe, if I understood the first part right, it was talking about how people who are actually vegetarian or vegan don't necessarily want these products to be super meat-like, right? Yeah. And so I would say, we certainly have the ability to create different types of products that have higher protein. So if we talk maybe I think I lost. Oh, it's back. A plant-based milk might be a little bit more desirable, and so looking at how to better solubilize protein rather than creating gels out of it, can we make it more soluble and gel and more stable in a beverage and tastes better, essentially, so that it tastes less beany and grassy in these other types of very different format. So you're still getting protein, but it's going to be more of a sweet type beverage and not at all like a meat product.
Okay, this is going to be our last question. If anybody else has any more, Mr. Chapa will be here for a little while after if you want to ask them.
Yeah. Hi, I have another question I just thought of. So on the slide with the nutritional info with the Impossible meat, you mentioned that there was one that there was a content in there that we wanted to reduce. Is there any particular reason why that one we want less? And is there a suitable replacement for it?
Are you talking about the methylcellulose? Okay, so the reason we want to be able to pull out methylcellulose is two basic things. So one, the ingredient statement will be shorter, and consumer studies show that that is better for purchase and repurchase, actually. So that's not a very good scientific reason, but it is a very good commercial reason, actually. So, and then the other thing is simply you don't have to have it. So there's been this belief that it's absolutely essential, the only way of creating gels, but that's not true. You can actually valorize a component that needs to be in the food to begin with, which is that soy protein concentrate, or it could be any other type of plant protein concentrate or isolate, right? It could be pea, fava, lentil, what have you. But the point is, by using an enzyme, you can actually eliminate a component and get more out of a component that's already there. Thank you.
Thank you again, Mr. Chapa, and thank you all for listening. We hope you enjoyed the talk and learned something new tonight. Thank you to the museum's digital team for assisting with the presentation, and to the Daily Planet Cafe staff for hosting us. If you enjoyed this presentation, you can find archived content from previous Teen Science Cafes on the museum YouTube channel, and this presentation will be there soon too. We invite you back on Friday, February 2nd, which is Groundhog Day, for our next presentation. The museum's mammalogy research curator will talk about groundhogs.